Now we shall see the history of lighting, and particularly the history of lighting sources, the history of lighting optical systems, the history of the systems for lighting, and the history, finally, of material and processes. So, first, we shall see the history of lighting sources. At the beginning of automotive, the lone possible source was candles, emitting roughly one candela, as this unit was created with this reference. Another important unit for light is the lumen for the quantity of light. It is defined as the light from a source having of one candela and received by a steradian, so by the surface of 1 square meter on a sphere with 1 meter radius. The total surface of this sphere is 2p, so roughly 12. And so a typical candle of 1 candela is emitting 12 lumen, still so very weak compared to modern lighting. After were introduced oil lamps, better will mainly to be seen and not really to see. Okay? At the end of the 19th century, Blériot proposed to use carbide lamps. Carbide was already used, for instance, in mines, and it's a light that is produced by the combustion of acetylene gas that is itself produced by a water put on calcium carbide. We have naturally much better illumination than oil, but it's still very weak, perhaps around 50 lumen. And a simple parabola with a flame roughly focused was used for the optical system. The glare, because at that time we had already some problem with the glare, was avoided by manually turning the lamps on some automotive systems. And Ford began the use of carbide in 1908 on the very famous Model T. Finally, this system was replaced in 1915 by filament system, so with tungsten. It was the first attempt on the Columbia in 1898, but the first real use was with the Ford T. And after, this technology was also used in Europe, for instance, with Carrello and Bosch. It was a very important improvement at that time, but there were really no solution for glare at this time. With a parabola and with a tungsten filament placed at the focal point, the rays are going out of the system in a parallel directions. So it's good in a high beam, it's good to have a good range, but when we have other users, we are glaring them. And at this period, despite the relatively weak output of a light, we had complaints about glare. And the question was, how can we have a system that is not glaring over users? The issue concerning the glare was solved in 1924, both by Osram and Phillips, with the invention of bifilament sources. The I-beam filament was still placed at the focal point, but another filament placed ahead for the low beam was used with a shield. So the rays going up to the upper part of the parabola were going down on the road because the beam was convergent, and the rays normally going to the lower part of the parabola were blocked by the shield, avoiding in that case to glare the other users when we were using these filaments. In 1940 appeared Silbeam, mainly in America. The target was to decrease cost by standardization and to have a stabilized quality. To realize this Silbeam, glass was used not only for the front lens but also for the reflector. and in fact it was a kind of big bulb with filament inside naturally, with reflector made with glass, with metallization to reflect light, and with some striation on the front lens. It was a system having at the beginning only one diameter, but after another diameter appeared. And the differentiation for style was in that case mainly produced by the bezels, the optical unit being standard at that time. Till 1957, the beam was flat. We had cutoff to avoid the glare for others in low beam, positioned at -1%. But the visibility was not good enough, particularly on the right side, to avoid the dangers from pedestrians or cyclists. And so appeared in this period the bulb called R2 or Code European, with a power in low beam of 40 watts and a flux of 675 lumen. The high beam being at 45 watts and with a flux of 860 lumen. This asymmetric low beam with a cutoff of 15 degrees in the right area improved significantly the visibility distance in this position. In 1962 appeared halogen sources. It was a very important improvement for both performances and durability. First appeared H1 with monofilaments. The principle of halogen is the redeposition of the evaporated tungsten on the filaments. Thanks to this system, the efficacy was doubled at 1,500 lumen for the H1. In 1969 appeared the H4 with two filaments, one for the low beam with 1,000 lumen, one for the high beam with 1,650 lumen. The color of the light now for halogen is roughly at 3,200 Kelvin degrees. But the majority of the energy is still emitted in infrared, so not really visible and so not really useful. In 1991 appeared high-intensity discharge bulbs, also called the xenon bulbs, with a target to improve both performances and durability. We had different versions of these xenon bulbs, with and after without mercury due to environment reasons, with or without high voltage signature included, and with specific version for reflectors. With xenon bulbs, we have the first phase. We are creating an arc with 15,000 volts between two electrodes. After, we are evaporating metal halides inside with relatively high power of 80 watts. And in the first phase, with 35 watts, there is a stabilized luminous flux at around 3,000 lumen, twice the level of halogen flux. The interest was the duration, with 2,000 hours, 3 times the level of halogen bulbs, and also a color temperature that is whiter than halogen with a level of 4,200 Kelvin degrees instead of 3,200 Kelvin degrees for halogen. But the cost of ballast to manage these 3 phases, the cost of the bulbs, was relatively high, and so the market for this system was relatively limited, never better than 15% of the total market share. On this slide you can see the difference of color between an halogen, relatively yellow, compared to the xenon, naturally much whiter. After the history of lighting sources, we shall see now the history of the different lighting optical systems that were used. In 1981 appeared the projectile lamps, also called elliptic systems. For the first time on the Quartz, Opel Calibra or BMW 7 models. The targets were to improve performances thanks to the fact that with elliptic systems we have an efficiency much better than parabola. We are able to catch roughly 85% of the light instead of 45% for parabola. Thanks to this, we can decrease the size of the optical system, now particularly the aids. The aid with parabola is limited, and we have a minimum of 90 mm until 100 mm to have a minimum level of efficiency. Where with elliptic system we can have a frontal lens, a lens for the optical system of 60 mm. With an elliptic system we have also an elliptic reflector, and at the focal point of this elliptic reflector we are placing the filament of the bulbs or the arc for xenon. At the second focal point we are placing the shields when we are naturally in low beam, and we have another lens, and the focal point of the lens is corresponding to the second focal point of the elliptic reflector, so that we can project the image of the upper part of the shields. Naturally, when we are in high beam, we are moving the shields by a solenoid or by a DC motor, so that we can, with the system, we can have both low beam and high beam functions with an elliptic system. In 1988 appeared complex surface or freeform system, first introduced by Citroën and Valeo on XM. The target was to reduce the size of reflector and keep low costs by using a system similar to a parabola, but with a much better efficiency. With a parabola, as we have seen previously, we are needing in low beam to avoid glare, we are needing to put a shield, and so with this shield we are losing roughly 45% of the total light. So the principle here was to use the interior surface of a reflector in low beam by the definition of a specific shape, and with this specific shape we are aligning all the images on the cutoff so that we can avoid to glare the others, keeping a very good efficiency by the fact that all the surface of the reflector is used. On this slide you can see a comparison of the efficiency of different optical systems. With a projector system we have to consider the efficiency of the elliptic reflector by itself. So we have a solid angle of 0.85. We have metallization, and so we are losing 10%, so the reflection is 0.9. We have a shield, and with a shield we are losing 45% of the light, so we have an efficiency of 0.55. We have the internal lens transmission. We are losing 50% of the light, and so the efficiency is 0.85. And we have finally the external lens, where we are losing also 15% of the light. So globally we have an efficiency of 0.3. With the H4 system we have a solid angular ratio of 0.45. Reflection on the reflector is 0.9, shield effect 0.55, and so with a lens transmission of 0.85 we have a global efficiency of 0.19 only. With the complex surface systems we have a solid angle ratio of 0.45, a reflection of 0.9, a lens transmission of 0.85, 0.85, and so a global efficiency of 0.34. We have to say that for complex surface or freeform systems, the efficiency is mainly depending on the size of a reflector. 0.34 is for a level of dimensions, but this can vary much more than for projectile system. But projectile system and complex surface system are roughly at a similar level. In every case, much better than H4 system for low beam. Now we shall see the history of lighting system, and when we are speaking about lighting system, that means that system not only including sources and optical system, but also including some electronics. First, automatic leveling systems that appeared in the 80s. The targets were to keep good aiming despite the change of a load or change of braking or accelerating conditions. Automatic leveling is obligatory in EC regulation for HIDs or xenon systems and LEDs, but not for halogen, having still a derogation. We have two types of automatic leveling. We have a static type that is only for the variation of a load, and we have the dynamic systems for correction, both for the load naturally, but also for braking or accelerating. The realization of leveling system is done by putting some sensors on front and rear axles. We can, in some cases, avoid to put some sensors on front axles, but with more limited results. We have the information from the speed and vehicle trim, and all this information is sent to an electronic unit that are calculating how the system has to be aimed to maintain a good aiming. And we are using some DC or stepper motors in the headlamp to adjust the position of the reflector inside the headlamp. In 2003 appeared the bending lights with a target to improve the visibility range in the curve by putting more light in the direction where the car will go. We were using two types of systems. First, the static bending lights, that is realized by the installation of fixed beam to enlarge the left and the right range. And this system is particularly useful for small radius curves or at crossing. And the other type is called the dynamic bending lights. And this is realized by moving at the beginning, moving generally a bifunction HID unit inside the headlamp, now more naturally with LEDs, and moving till an angle of 15 degrees. And this is particularly useful for large radius curves at relatively high speed. Naturally, the information that is used is the information of the driving wheel angle. On this slide you can see the benefit of bending lights. With bending lights you are putting more light in the direction where you are going in the curve, and so you have a better visibility distance, a better anticipation of danger. Bending light was an anticipated function of most global system called adaptive front lighting system, with a regulation appeared in 2007. The target was to have several beams, each adapted of specific environments. For instance, for motorway, to improve the visibility distance, a new regulation was created with the possibility to raise a little bit the cutoff. Instead of minus 1%, the cutoff has the possibility to be raised till minus 0.4%, and with the possibility also to have a higher level of intensity. We have the possibility to improve the visibility distance from 60 meters to 120 meters with these functions. Naturally, this can be realized by specific projector modules, for instance, by a specific shape of a rotating drum, or with LEDs with a dedicated module. Other functions were created, adverse weather light, country light, or tone lights, but that were clearly much less used than bending light or motorway lighting. Adverse weather light is targeted to be used during difficult conditions, with rain, for instance, and the targets were to have a better visibility for the driver and to reduce glare for other users by reducing the reflection of the light on the road. So the realization was relatively difficult, and with halogen and xenon there was not really the possibility to realize such functions. Now, naturally, with high definition system, it's much more possible and easy to realize this kind of beam. Country light was targeting to be used in country by illuminating the left and right edge on the road more brightly and widely. So it's actively between 50 kilometers and 100 kilometers. In town, a specific beam was defined to better see pedestrian and reducing a little bit the glare by reducing the level of lights in the cutoff area. We shall see now the history of materials and processes used for lighting. During a long time, reflectors were done with steel, and we were using lens, a glass lens. The interest of steel and glass was their temperature resistance, because at the time we were using tungsten and then halogen systems, and the round shape being the easiest to be produced. In 1940, steel beams were dominating in America, particularly in Japan, using glass, as we have seen previously, both for reflector and lenses. In 1961, due to style, there was an evolution towards a rectangular shape, with introduction, for instance, by Citroën of the ME6, with still some striation of the lens for the distribution of light. But with steel, we have still an important limitation concerning the style, and so the target were to enlarge these possibilities by introducing plastic reflectors. The beginning of plastic reflectors in the lamps was in the beginning of the 80s by the introduction of DMC, or dot molding compound, or thermoset reflectors. The interest of thermoset reflectors are their good thermal property, because the temperature resistance is around 200 Celsius degrees. We have a very good stability, a good mechanical stability, and a good shape respect. Nevertheless, we need to have a varnish on DMC reflector before metallization. Steel reflector was still used during this period for elliptic system. As for elliptic system, due to the relatively small size of reflectors, the temperature is higher and DMC cannot really be used. Now we are using more and more thermoplastic reflectors we had the possibility to use some thermoplastic with halogen, but it was relatively difficult due to temperature resistance. Naturally, now with the introduction of LEDs, this temperature constraints is much lower, and so thermoplastic reflector can be used more easily. And all these family of plastic reflectors is allowing naturally much more freedom for style and better possible ratio for the length compared to the height. Another important evolution or revolution was the introduction of plastic lenses for lamps in 1983 and 5 years later in Europe. The interest of plastic lenses is naturally the possibility of style. With glass we have some limitation concerning the height, some limitation concerning the ratio height compared to the length, but we have no more with plastic. Polycarbonate is a good material for plastic lenses as it has a very good mechanical resistance. Nevertheless, polycarbonate is sensitive to UV, is sensitive to abrasion, sensitive to solvent, and so we need to put varnish. So hard coat varnish is systematically put on plastic lenses. At the beginning of 2000s appeared the clear lenses. That was another very important evolution because we had to solve many problems, particularly an optical problem. All the distribution of light has to be done by the reflector, and so we are needing a specific we needed a specific optical definition for the reflector. And the second very important issue was industrial, because all the plants needed to be transformed to improve the quality, to avoid any defects on the reflector and on the lens, to have a perfect product for the perceived quality. We have seen in the past slides the main facts in relation to the history of lighting. On this slide, you can see that there is a kind of acceleration for the introduction of new technologies. For instance, between the introduction of tungsten and halogen, we had 64 years. Between halogen and xenon, 39 years. Between xenon and LEDs, 16 years, and so on. For the other function, for instance, that we shall see in the next chapters.